So welcome all to week 7 tutorial for the course Essential Mathematics for Machine Learning. I'm Pintu Kumar. I'm a PhD scholar at IIT Bombay. So from week 7, we are starting with second half of the course. So in the first half of the course, we did linear algebra. In second half, we will do some basics of calculus that is essential for mathematics, this machine learning. And also we'll do some probability and statistics in later weeks. Okay. So this course or this particular lecture will today cover some basics of calculus. So if some of you are familiar with this deep learning, so most of the common new deep learning architecture use gradient descent for optimization. Okay. You might have heard something like Adam optimizer, right? So these things we are going to cover. So how do you optimize? How do you get the best prediction? So those things we are covered. So today's tutorial is going to be very basic. We are going to define what is function, different kinds of function. Then we will go to defining limits of a function. Then we will define continuity of a function, differentiability of a function. We'll slowly go on to partial derivative, then to gradients, Jacobian, Hessian, and those kind of things. So this might be a slightly lengthy lecture. So at any time, if you have any doubt, please unmute yourself and ask, or you can also type it in the chat box. Okay. So first of all, let's look at what is function. You have done linear algebra, right? You have done what are linear transformations and those kind of things. So you already have some idea of what a function is, but formally, if you define what is a function, so a function is nothing but a variable y that depends on a variable x. So y is something of x. You can do all sort of things with x, but the only condition is each value of x uniquely determines a value of y. So for every value of x, you should get a unique value of y. If you have such a relation, then y is a function of x, and we generally denote it as f of x. Okay, so y is a function of x. So for example, if you look at square root of x, like if you have, let's say, square root of 4, it can, if you allow it to take both the values plus 2 and minus 2, then it is not a function. But if you restrict, let's say that you only want positive values, then you can define it as a function. Okay. So a function can only take unique values. So no value of x can map to two different values of y. Okay. So what is domain, codomain, and range of a function? You might have done it in high school, but I'll reiterate. So I'll probably define domain and range, which are more important. So domain, let's say uh, y is some relation of x. Okay. Then the space in which your x lies is called the domain. The set of values from which you can sort of pick your x, from which you can pick your x, is called domain, and the set of values that y can take is called range. Okay, values that y can take. Okay, so let's look at these two examples. We have to find the domain and the range of these functions. This might be pretty elementary, but let's begin slow. We will definitely cover more advanced topic towards the end of this tutorial. Okay, so first question says 2 plus under root of x minus 1, and we have to find its domain and range. Okay, so let's look at domain first. What are the possible values that x can take? Okay, so we could have allowed all values of x. The only problem is the square root of x minus 1. Okay, so square root can't have negative value in it. So what we can have is that x minus 1 should be greater than equal to 0. This is the condition that we have to impose because of the structure of the function. So this means x should be greater than equal to 1. So domain of this set is 1 to infinity. You can take any value greater than 1, that will be in your domain. So what will be the range? So this is 2 plus under root of x minus 1. So if you keep increasing your x from 1, you will keep getting higher and higher values from here, and it will be added to 2. So the range is 2 to infinity. This is the range, right? Similarly, let's look at the b part. B part is x plus 1 divided by x minus 1. So you know that if you divide anything by 0, it is not defined. So if you divide anything by 0, this operation is not defined. Okay. So you can't divide anything by 0, right? So that's why we can't have denominator to be 0. So x minus 1, we don't want it to be 0. This implies x is not equal to 1. So domain for this particular function is nothing but r minus 1. This symbol, I think most of you would be familiar. This symbol is set minus. This means you are subtracting this particular element from your set R. Okay. And what is the range of this function? So in order to calculate the range of this function, we will look at all sort of values that this function can take. So let's say my x plus 1 divided by x minus 1 takes value c. Okay. So what are the possible values for c? Let's try to solve it. This implies x plus 1 is c times x minus 1. This would give us x 1 minus c is equal to this is minus 1 minus c, right? So this would give us x is equal to 1 plus c divided by c minus 1, right? So if you want a value c, you pick this particular x, then your function will return this value. Okay. So the range is again you can't have denominator to be 0. So your range is again r minus 1. Okay. This means that like if I want value of my function to be c, then I should pick this particular value of my x. Okay. For example, if you want c to be 2, then you should pick x to be 3 divided by 1 is 3, right? So you can't have any x for c is equal to 1 because this thing is not defined. So this is my range set. Okay. I have included few more examples over here, but I'm not going to cover them. You can solve it on your own. Okay. Okay. I don't think there should be any doubt till this point, but if please there is any doubt, I request you to please unmute and ask. Okay. Now we have a categories of function that is useful at different parts in machine learning. So what is an identity function? Okay, one more very small thing. Over here, all the examples that we covered were functions from R to R. That means they were functions from same space to same space, but it is not necessary. You saw many kinds of linear transformation when you were doing linear algebra. So your functions can be from any arbitrary set x to any arbitrary set y. Okay, so this is very much fine. Okay, so an identity function is a function from set to itself. First thing is that it should be set to itself. And second condition is f of x is just x. Okay, so if you give it x, it will return you x. This function is called identity function. Okay, so this is like the identity of vector space that you did when you defined vector space, existence of identity element. This is similar to this. This is a space of all functions from x to x. Then this is the identity function. This is also a vector space, and you can see this as an identity element. Okay. Second thing, I think I haven't mentioned the topic, but inverse of a function. I'll talk about when inverse exists, but inverse of a function. Okay. So let's say your f is a function from x to y, then g a function from y to x is called inverse of f if what is the condition? Condition is that f of g of y, okay, g of f of x is equal to f of x, yeah, this will be x, or g of f of x is identity function. So if you compose g on top of f, if that composition is an identity function, then you say that g is an inverse of f, and it is true other way around also. F of g of y is also y. Okay, so we denote this thing by g of f, and this is f of g, right? Both those things should be equal to identity. Okay. Another very elementary definition is odd and even function. Okay. So first thing, it is not necessary that any arbitrary function belongs to one of these two categories. So it is not necessary. A function can be not even and not odd. So it can be anything apart from odd and even. Odd and even function is a very small subset of all set of functions. So see of these cases. Okay. So first of all, let's say what is an odd function. Okay. It's a function from x to x. You want it to be from same space to same space, satisfying the property. If you take f of minus x, this should be equal to minus of f of x. Okay. So the negative just comes out. I'll give you an example. Example is your simple identity function x. So if you take f of minus x, it's minus x, which is same. Another example is f of x is equal to sine of x. So if you take sine of minus x, this is equal to minus sine of x, which is equal to minus f of x, if this was your f of x, right? Sorry, this is f of minus x, right? So these are two examples of odd function. Something similar is definition of an even function. Okay. So even function will consume the negative sign. So it's also a function from x to x, having the property that f of minus x is f of x. Okay, so if you even if you give the negative sign, it will consume that negative sign. Okay, so for example, if you take f of x is equal to x square, so this would be nothing but so if you take a minus of f of x, this is minus x square, this is x square. And another example is cos x. So if you give cos minus x, this is equal to cos of x. Okay. So one can think how would a graph of such function look. It's not very difficult to see. Let's try to draw. So let's say this is your two-dimensional plane, and this is some function f that you know is an even function. Why am I not able to change the color? Okay, so let's say this is some plot of your some even function. Then whatever is the value at this point x, the value would be same at this point minus x also, right? So we will have a mirror image. My drawing is not that great. So you just see that this is a mirror image along the y-axis for an even function. Okay. And for an odd function, let's try to draw it here. Okay, it's not going to, no, it's not going to any other pen. I've changed the color here only. Okay, let's say this is the plot that you have drawn. Then you will have a negative y, right? So it is sort of a mirror image along this line. Is it? No. It's not a mirror image along this line, but I hope you understood what I'm trying to say. I don't know how to erase it now. Okay. So it's something like you take first its mirror image along this. I'll just restart this one note. It is causing some error. I'll share the screen again. It's like taking its mirror image first along x-axis and then against this y-axis. Okay, so this is how your odd function would look like if you plot it on graph. Okay, then we have a class of function called one function, onto function, and bijective function. We'll quickly go over it. Okay, so you might have seen these kind of diagrams in your school when you denote a function. So in a function, what happens is these are your x or the domain. This is something that is known as codomain, or you can refer it as a larger set of a range. Okay, so every element of x would be mapped to some unique element, right? Probably this one goes to this one goes to this one again goes to this one goes to this. Let's say something like this. Okay, so this is a relation that we are drawing, how x is related to y that we are representing. Now a function is called 1 if every element over here, every y, has a unique pre-image. So that means that no two different x are mapped to same element. So this is not a 1 function. To make it 1, we should map this particular element to some other element. Okay, because every element in y should have a unique pre-image. Okay, or no two elements in x should be mapped to a same element. Then that kind of function is called a 1 function or 1 function, right? So a very quick tip: if somebody asks you to prove uh, a function is 1, how you approach that thing is, so you let us assume that f of x1 is equal to f of x2, and then you do something, 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 and you should end up proving that x1 is equal to x2. If you are successful in doing this, then you have successfully proved that your function is an 1-1 function. Okay. Okay, now what is an onto function? I'll copy this particular image only over here. Okay, so you can see that over here we left out an element, this particular element. So if we had, let's say, one more element and we map this to this particular element, then all the elements on y side was also occupied, right? Then those kind of function are called onto functions. Okay. More formally speaking, every element of y has a pre-image. Then that function is called an onto function. For example, let's say consider an example of x square. Over here, if you consider this negative y direction, you don't have any pre-image, right? So x square is not an onto function. Okay. Whereas if you take x cube, your curve would look something like this, and you have pre-image for every y, right? So this kind of function is an onto function. Okay. By the way, your x square is also not a 1-1 function, because let's say at this point you have two images. So, right, corresponding to this point and this point, you have same value of y. Okay. So x square is not a 1-1 function also, whereas x cube is a 1-1 function. Okay. Now, what is a bijective function? Any function which is 1 as well as onto is called bijective function. Another name for bijective function is called invertible function. Okay. So a few moments ago we talked about what are inverse of a function. So you can find inverse of a function only for bijective functions. So inverse exists only for bijective function. Okay. So you can't inverse every function, you can inverse only bijective function. Okay. Any doubt till this point? Okay, thank you. So we'll go ahead and talk about something that is called limit of a function. Okay. So what is limit of a function is, let's say you, for some reason, you can't evaluate your function at point x. Okay. So what you want to do is, rather than evaluating this function at point x, you, let's say this is your point x, you want to approach this x, you want to keep coming closer to x and see how the values of x behave. Okay. You want to keep coming closer to x and see how the values of x behave. The value that x attains in a very small neighborhood of x is called limit of that function at x. We'll more formally define it. Let's look at two motivating example why limit can be useful. Let's say you have a circle or any random curve. You want to find tangent to a point. Okay, tangent to a point is a line just passing through that particular thing, right? So how you can obtain a tangent is, you can pick any 2 points. Let's say I pick this P and Q. You drew a second line. Then you made the point Q closer to your point P. Okay. Then you again obtained a second line passing through P and Q. Then you again did the same thing. Now you see that we are drawing line through these 2 points. Okay. When we reach the point P, we can't draw a line passing just through one point, right? So what we are doing is we are limiting this thing. So we will keep drawing these lines by decreasing the distance of Q from P, and we will get the tangent line. So we can obtain tangent lines via limits. Okay. By the way, this image is taken from a book titled Calculus by Anton and Davis. I won't recommend right now reading that book because just to introduce limits and those kind of things, it goes to 140 odd pages. So it's not very much recommended that you spend that much time understanding that. Whatever is essential for machine learning would be covered in this lecture course itself. So you can avoid going to the book right now. Okay. But if someone has a special interest, that person can refer to that. Okay. Second example is, let's say you want to find the area under the curve. Okay. So calculating integration, let's say for some function is not possible. You want some numerical techniques to find area under the curve. So what you can do is you can draw such rectangles. Okay. And then add the areas of these rectangles. But then you will have some small error. For example, this graded shade portion, this portion, you will have these kind of errors, right? Over here, over here. If you decrease the size of these strips, right, then you will have a lower error, right? The error has reduced. Now, if you limit your strip size to 0, then you will get an exact area of your, right, the area under the curve. Okay. So this is another example where limit can be useful. Okay. So let's sort of formally define limit. I'll first define it for an uh, R to R function. Let's say f is a function from R to R. Okay. So this is your R. This is also R, but let's say this is X, this is Y. And you have, let's say, a function of this form. Okay. Or we can have some function with some steep curve, let's say, something like this. Okay. This is curve only, there is no sharp point thing over here. So let's say this is your X. Okay. So how do we define limit is, there is something called left hand limit. Okay. Left hand limit is, if you keep coming closer to X from the left hand side, what is the value of X that you are getting? Sorry, f of X that you are getting. Okay. So left hand limit is defined as f of X minus H minus f of X, sorry, yeah. This is what you have as your limit. H tends to 0. Okay. And right hand limit is, if you keep coming closer to this point from right hand side, then what is the value of your function? Okay. So if you are decreasing your H towards 0, then you are coming close to X from right hand side. And if your left hand limit and right hand limit are equal, that particular value is called limit of your function at X. Okay. Okay. This you might have done in your school, but I'll define how do we define limit for an higher dimension function. If you have, some of you is from BSc mathematics background, they might have done in some engineering mathematics course also. It is possible that it was covered, but I'll try to cover. Okay. So let's say, okay, this is a two-dimensional figure that I can draw, but let's say this is your domain. This is an R cross R. So we have a function from R2 to R. This is nothing but a three-dimensional function. So this is something like f of x comma y is some z. Okay. So let's say you are drawing an can I draw? So a figure something like this, some hemisphere kind of a thing. Okay. So this, imagine that this is a 3D figure. Okay. Now I want to find its limit at 0, comma 0. Okay. So in two dimension, I had only two paths to approach x. One was from right hand side, one was from left hand side. Now when you have a two-dimensional domain, you can, let's say, approach this point via this x-axis. Okay. Also, you can approach this 0, comma 0 via y-axis, from negative direction of y-axis, from negative direction of x-axis. Also, you can approach through any random path going to 0, comma 0, right? So you have infinitely many paths, okay? And no matter what path you choose, if you get a unique limit, then only you say that limit exists. And whatever is the unique limit that you are getting is the value of the limit. Okay. We will solve one question where we will disprove, we will show that the limit does not exist at 0, comma 0 in that case. Okay. Okay. So let's look at these simple examples. You might have done it in your high school or something like that. So first of all, first question is find the limit of this particular example. Limit x tends to 3. If we directly substitute the value of 3 in it, we will get denominator to be 0, which is not defined. So we can split the top. So what we will do is x square minus 3x plus 9 divided by x minus 3, which is equivalent to taking x minus 3 minus 3x minus 3 divided by x minus 3. The top is x minus 3 whole square. I think I have not made any mistake here. Divided by x minus 3. This things gets cancelled. So this, whatever we are left with is x minus 3, which is again 0. So you can have such kind of simplifications, and such simplification, for example, will exist over here also. Let's look at B part. B part is limit x tends to minus 4, 2x plus 8 divided by x square plus x minus 12. Okay. So if we put value of minus 4 in denominator, what we would obtain is, this is 16 minus 4 minus 12, which is equal to 0. You can't have denominator to be 0. So let's try to split it. This is equivalent to limit x tends to minus 4, 2x plus 8 divided by x square plus 4x minus 3x minus 12. This is 2x plus 8, x plus 4 minus 3x plus 4. So this is 2, if you take common, this is x plus 4 divided by x plus 4 multiplied by x minus 3. X plus 4 and x plus 4 gets cancelled. We are left with 2 divided by x minus 3. And if you put the limit now, you will get minus 2 by 7. So this is the limit of this particular equation. Similarly, you can solve over here. You will get some terms cancelled and you can work out accordingly. Okay. Okay. Next topic is continuity. Okay. So when do we call a function to be continuous? I won't go into very technical definition, but if you look at a function from R to R, you say that a function is continuous if you can draw it without lifting a pen. So what does this mean is intuitively that your functions don't have sudden jumps. For example, let's look at this function. It starts here and then suddenly jumps here and then goes like this, something like this. Your function, if it has this kind of property that it is suddenly jumping, then it's not continuous. It should be a smooth function. It can be drawn with just a pen. More technically defining, okay, one more intuition is if you change your x a little bit, then your y should also not change by much, change by a lot. For example, in this black example, if you moved your x, let's say from here to here, the change in x is very small, but change in y is very large. So you don't want that kind of situation. If you perturb your x a little bit, then your change in y should not be very large. Okay. Now, theoretically defining, you say f is continuous at x if first condition is limit exists at x. So if you are either coming from left hand side or you are coming from right hand side, you should attain same value. If you look at the black example, this condition was violated. If I let's say this is my point x, if I approach this point x via this thing, let's say this is value 1 and this is 1.5, I'll reach a value of 1. If I come from right hand side, I'll reach a value of 1.5. So limit also don't exist for this particular function. So the first condition that you should have is that limit exists at x, and second condition is f of x should be equal to limit, let's use a notion a, limit x tends to a, f of x. Okay, at some point a, this thing should hold, so this will also be a. Okay, so what I mean is, by second condition, what I'm inferring is, let's say you have a plot something like this. So you are going like this, and suddenly at some point your value jumps a lot. Okay, and then again you are continuous. So over here, limit exists at this point. Let's say this is a, limit exists at the point, as even if you take the left root or the right root, you're reaching the same point, this hollow thing. But the value of the function at this point has taken a sudden jump, which is not allowed for continuous functions. Okay, continuous functions are very beautiful functions that you can draw with your hand. Okay. Any doubt in continuous function before we move to derivation, this derivative of a function? If you have any doubt, you can ask. Now is the time. Okay. Let's define what derivative is. Okay. So geometrically speaking, derivative of a function at any point, let's say x naught. In this example, in this figure, we have x naught. If you draw a tangent line at this point, x naught comma y naught, this derivative is slope of this tangent line. Okay. So how is your function inclined, whether it is increasing at that point, decreasing at that point, how fast it is increasing? All those kind of things can be obtained from slope of the tangent. So if your function is growing very fast, your slope would be very steep. If your function is slowly growing, your slope would be much like flatter. Okay. So to do these kind of things, we define derivative. It is nothing but the slope of the tangent. Okay. Now, let's say this is your line. You only know one point that lies on that particular line. Okay. But in order to calculate the slope, you should know at least 2 points, right? Then only you can calculate slope of this line. Okay. How do we go about this is, let's say this is some point Q, this is P, and we can have, let's say this point is x, then what is the slope of this second line that is written over here? The slope is f of x minus f of x naught divided by x minus x naught, right? This is how you can obtain the slope of this line, okay? Or if we move this q closer, let's say this is q1 and this is x1, then again you can have of x1 minus f of x naught divided by x1 minus x naught. So what we will do is, we will limit this distance to a very small number, okay? We'll limit this thing to 0, okay? So then what we can obtain is, we will limit this x1 minus x naught to 0. So derivative can be defined as limit some, let's say h tends to 0, okay? We take f of x plus h minus f of x divided by h. So we are just taking 2 points at an h distance, then we are looking at the slope of that particular second, and we are limiting h to 0. This is how the derivative is defined, okay? An alternate definition is what is written over here. Here we have written x tends to c. That would mean that this x is x plus h in our case. C is the point at which we are calculating the derivative, and x minus c is nothing but the h itself, okay? So these are two are equivalent definition, okay? Now there is one more small thing. Whatever we did right now, we could have done it the other way around too, right? Let's say I picked a point over here, I drew this line, and then limited this distance, okay? So whatever we did initially is called right hand derivative, because we were approaching this point via right path. Again, we can approach it via left part, and we will have f of x minus h minus f of x divided by h, and limit h tends to 0. So if my left hand derivative and right hand derivative both matches, that is the value of my derivative, okay? That is the value of my derivative, okay? I know all of you know how to find derivative of basic functions. These definitions were like included in the course, so that you know the idea behind it. Sometimes you might have to write some proofs if you are doing research or those kind of things. There, these kind of things sometimes come handy, okay? And you should understand the idea behind what is derivative and what is partial derivative, those kind of things, okay? Now there is something that is known as partial derivative, okay? Before going to partial derivative, uh, there is one interpretation of a derivative. So let's say your derivative at some point x is something, okay? So its interpretation is, if you move your x a bit, then how fast does your y change? This is another interpretation of derivative, that if you move your x a little bit, how fast does your y changes? So it's going slow, it's growing very fast. Those kind of things can be obtained via derivative, okay? Now when you have uh, function in 2 dimension, let's say it's a function of x and y is equal to z, then if you say that we move a bit and see how much my z is changing, a more sensible question to ask is, let's say if I move just my x a little bit and keep my y fixed, how much my z changes? And a similar question that can be asked is, if I, let's say I move my y a little bit and keep my x fixed, how much my z changes? So this is what is defined as partial derivative. So partial derivative with respect to x is given by, if I perturb my x a little bit and keep my y fixed, what is the derivative in that particular direction? Okay. And similarly, you can define your uh, partial derivative with respect to y. Okay. An easy way to calculate this is, let's say you have a function of x comma y. Okay. And you want to calculate, so okay, this is represented by f of x. This is just a notation. So what you can do is, you can just treat your y as a constant. You don't see y as a variable. Then you calculate the derivative of f with respect to x. Okay. And then you evaluate this derivative at x is equal to x, whatever point is given to you. Okay. Okay. So this is the idea behind partial derivative and derivative. I think you might be aware about some rules of derivative. So let's say you have a function f of x. Its derivative is also written as f dash of x. Now if you have alpha times f of x, and if you take its derivative, this is nothing but alpha times f dash of x, right? If you have, let's say, derivative of f of x plus g of x, this is also nothing but f dash x plus g dash x. Okay. Now, two important rules. One is called product rule. So this is product rule. Okay. So if you have, let's say, d by dx of fx into gx, then this is given by f of x into g dash x plus g of x into f dash x. So one of you keep constant and then you take the derivative further, plus next time you keep the other one constant and take the derivative further. Okay, this is called product rule. Similarly, there is this quotient rule. So you have f dash x minus into g of x minus g dash x into f of x divided by g of x square. Okay. Okay. So we will solve these questions. Okay. First of all, let's solve 12 and 13. Then we will come back to example 9. Okay. So this is asking us to find second order partial derivative f of x for this particular function. So we have to find f of xx and f of yy. So in order to, what is f of xx and what is f of yy? So if you take first order derivative, you obtain f of x, right? This is again a function. If you again take its partial derivative with respect to x, this is f of xx. If you take again with respect to y, you can keep on adding those symbols. Okay. So let's first of all try to find f of x and f of y. So when we calculate f of x, we keep our y as constant and derivative with respect to x. So what would we obtain? We would obtain f of x is equal to 2x multiplied by y cube plus 4x cube y. Similarly, what we will obtain f of y is, now we treat x as constant and we will differentiate only with respect to y. This is 3y square x square plus x to the power 4, right? Now let's calculate f of xx. So this is partial derivative of f of x with respect to x, right? So it is given by 2 multiplied by y cube plus 12x square y. Then f of y is partial derivative of f of y with respect to y. This is 6yx square plus 0. This is how you can find partial derivative. Okay, let's do one more example. Just a second. Okay. We are given f of xy as y square e to the power x plus y. In order to find f of x, y, first of all we will find f of x. Now we'll treat y as constant, so it would be y square e to the power x plus 0. That is y square e to the power x, right? Now f of x, y would be derivative of this with respect to y. This is 2y e to the power x, right? F of x, y is 2 e to the power x. Okay. If you have any doubt, you can ask, and I'll solve this question. Okay, so we will not do the first part right now. You can show that this partial derivative exists at all the point. This you can show. The question that we are interested in is, why is it not continuous at 0, 0? I said when we had two direction, we can only approach from x or y direction. But as soon as we go in 3 dimension, we have arbitrary many paths to come from. Okay. So f of xy is given as minus xy divided by x square plus y square, right? Let's say we approach this 0, 0 via line y is equal to x. Okay, y is equal to x line passes through 0, 0. So we can come to this function via this line. Okay, so what would happen? So limit y tends to x minus xy divided by x square plus y square. If I replace now my y with x, the denominator is not 0, right? So we are good with it. So we can just replace these values. We will get minus x square divided by x square plus x square. This is x square by 2x square, and this is minus 1 by 2. Okay. Also, we can come to this line via path y is equal to 2x. Right? This is also a path that passes through 0, 0, and we can come over here, right? So limit y tends to 2x minus xy, sorry, this equal to won't be there, x square plus y square is given by, so this would be minus 2x square divided by x square plus 4x square. Now if you take out the x square common, this would be minus 2 by 5. Now you see that if we approach the same point 0, 0 on this function via different path, we are getting different limits. This means limit does not exist at 0, 0, and hence f is not continuous at 0, 0. Okay. So if somebody gives you some function like this in 2 dimension or 3 dimension and asks you to prove or check whether it is continuous or discontinuous, generally they will ask you to prove it is discontinuous. Then you can come up with two different paths for which your limits that you are getting are different, and you would be able to prove that it is discontinuous. Okay. Okay. So now we will go to a very important topic called chain rule. Okay. So I think when you will do deep learning course, you will take some time understanding gradient descent. And more than that, you won't take a lot of time understanding gradient descent, but time that you will take would be in calculating gradient for complex calculation of gradient. Okay, so I think my internet stopped working. So I'll repeat what I said towards the end. I'm not sure till what point did you hear, so I'll repeat myself. Okay, so what I said is now we are going to cover chain rule. Okay, so you know that most of these machine learning methods adopts this gradient descent method to optimize itself. Okay, so when you do gradient descent, you have to find the gradient. Okay, so if you have this multi-layer perceptron or the deep neural network that you called, these days you have many complex networks, right? So calculating gradient for them is based on an approach called back propagation. Okay, and that back propagation is nothing but a machine learning kind of a name for chain rule. So like people who do machine learning, they call it back propagation, but that is nothing but an use of chain rule. Okay, so understanding chain rule is very important if you want to understand back propagation and the working of gradient descent method. Okay, so if in chain rule anything is not clear, please request you to stop me there and ask. Okay. So till now, what we have done is, so we have some f of x, right? Or so we can find a derivative of f with respect to x. Another thing that we did was, let's say we have some function f of xy. We can find its partial derivative with respect to x. We can find its partial derivative with respect to y. Okay, these two things are higher partial derivatives. Now let's say your z is a function that is a function of x comma y. Okay, and x and y itself is a function of some t. Okay, so x is some function of x of t and y is some function of y of t, right? Then how do you find the derivative? Okay, so one simple option can be, so you replace x by x of t in f of x y, and you replace y by y of t, then you evaluate z in terms of t and you calculate its derivative with respect to t. Okay, but that sometime for complex function can be very complex. Okay, so this is not a suggested method. So to cope up with that, we have something called as chain rule for derivative. Okay, so if you want to find the derivative of z with respect to t, you first calculate the derivative of z with respect to x, and then you calculate the derivative of x with respect to t. Okay, so you see that these two terms are same. If you had normal fractions, you could have cancelled it out. That's the reason why they are written in that fashion. Okay, then to this you add its dependence on second term, del z by del y, dy by dt. Okay, for example, let's say if your z was a function of a, b, c, d, and all a, b, c, d were function of t, then del z, so this dz by dt would be dz by dA plus, sorry, so this would be dz by dA multiplied by dA by dt plus del z by del v multiplied by dv by dt plus dc by dc into dc by dt plus dd. D is not a great notion that I have chosen, sorry for that. And d, okay, this is dz by dd and dd by dt. Okay, so this is how you can operate on chain rule. Okay, so let's try both the ways. So right now we have z is equal to x square y, where we are given what is x and what is t, right? Sorry, what is y and what is x. So let's try to calculate z straight away. This is x square y, so this would be t to the power 4 into t cube. This is t to the power 7. So dz by dt is nothing but 7 t to the power 6, right? Let's go via chain rule. So dz by dt is nothing but dz by dx into dx by dt plus dz by dy into dy by dt. Okay. So what is dz by dx? This is x square y, right? So you just consider y as a constant. So this is 2xy and dx by dt is 2t plus x square, and this is your 3t square, right? Yeah. Now you replace the value of x and y. This is t square into t cube t to the power 5. This is t to the power 6, right? So this is 4 t to the power 6 plus x square is t to the power 4. 3t square is t to the power 6 plus 3t to the power 6 is 7t to the power 6. So you are getting the same answer, but many times calculating straight away something like this. So calculating like this might not always be great when you have complex functions. Right now we had linear things, so it was okay. Okay. So, okay. This is the graph that I want you to pay most attention to in this lecture. Okay. Now, and this, if you understand this graph, then back propagation will never be an issue for you. Okay. So earlier what we had is z was a function of x and y, and x was a function of some t. Okay. But now what I'm saying is x again is a function of more than one variable. X is a function of u and v. Okay. So how do we calculate this? Okay, so, and I'm interested in values del z by del u or del z by del v. So again, we take a very similar approach. So what it is del z by del x first, then del x by del u. Del means partial derivative, nothing else. Then again, you will have del z by del y into del y by del u. Okay. So if you look at this thing in calculating the partial derivative of z with respect to u, we sort of went backwards to x, then backwards to u. And this is somehow the idea of back propagation. Whenever you will do a machine learning course, you will appreciate this thing. Okay. So let's try to calculate these things. Okay. So z is e to the power xy. X is this, y is this. Okay. So let's calculate del z by del u only. So what is del z by del x? We'll treat y as constant. So this would be y multiplied by e to the power xy, right? Multiplied by, now this is x is 2u plus v, this is 2, del z by del y, again this would be x e to the power xy, this is u by v, okay. So if you treat v as a constant, this would be 1 by v, right? So this is what you will obtain, del z by del u. Similarly, you can calculate del z by del v. Okay. So again, you have a similar question where w is a function of x, y, and z, and you have to calculate del w by del u. This would be again nothing but del w by del x by del u plus del w by del y into del y by del u plus del w by del z into del z by del u. Okay. And you can calculate these values and replace the value. Okay. Any doubt till this point? If you have any doubt, you can please ask. Okay. Okay. So till now, what we had defined is something known as partial derivative. Okay. So in partial derivative, what we did was, if we move, so what is f of x? If we move slightly in x-axis direction, what is the change in function that you observe? This is what is f of x, right? And what is f of y? If we change a little bit in y-axis direction, what is the change in function that you observe? Okay. So now what we want is, let's say this is represented by d of u. What does d of u represent? If you have u as any arbitrary unit vector, it's any arbitrary direction. If you move in that particular direction, okay, what is the change in function? Okay, so this is what you have to obtain. So this is again given by, I'll just write it out in a different way. So this is f of x. You are calculating the derivative at x naught and y naught. Then it is f of x naught plus some h that is very small h times u1. So your u is given by u1 I cap plus u2 j cap. This is the direction, comma y naught plus h times u2 minus f of x naught comma y naught divided by h, right? And you take limit h tends to 0. Right? This is the derivative, and in the compact form it is written like this, where you calculate your function in this form, take its derivative with respect to s, and you replace s to be 0. This is same as doing this. Okay. Okay. So here is an example. So you have been asked to find the derivative at this particular point, but let's say you first obtain the arbitrary derivative. So what is f of x plus? So what you will do is you have to do this thing, del by del s, right? And f of x naught plus su1 comma y naught plus su2 at s is equal to 0. So this the quantity inside the braces is nothing but, so this is your u1, this is your u2. So this is x plus root 3 by 2 s, right, multiplied by y plus 1 by 2 s, right? So you have to take its derivative at 0. So this is, if you take the product, what you will get, this is dy ds of xy plus root 3 by 2 s into y plus 1 by 2 s into x plus this 2 multiplied root 3 by 4 s square at s is equal to 0. Now you take its derivative. Okay, so you take its derivative is given by xy would become 0 plus root 3 by 2 y plus 1 by 2 x plus root 3 by 2 s at s is equal to 0. S, if you replace to be 0, you will get nothing but root 3 by 2 y plus 1 by 2 x. Now you were asked to obtain this value at 1 comma 2. So you can replace your x to be 1 and y to be 2, and you will get root 3 plus 1 by 2. This is the answer that you. Okay. So this is how you can obtain a directional derivative in any arbitrary direction. Okay. This was one method. You would have heard gradient many times, at least I have said it many times. Now we will see what is gradient. Okay. So what is gradient is, let's say you have a function. So now I'll define three things. First is gradient. Okay. Second is Jacobian. Third is Hessian. You please focus also on uh, like if I have function from where to where, and when I can define Jacobian, when I have to calculate Hessian, when I have to calculate gradient, you please keep and focus on that also. Okay. So let's say you have a function from R into R. Okay. So something like this. So Z is equal to f of x1, x2, xn. So you have a function of many things, but at the output level, you will get only one value. This is similar to what you obtain in machine learning, right? So you will have many features. You will do something, and at the end, you will have only one loss function that you will have with you, only one value. Okay. So gradient of f, this is how you represent gradient of f. This nabla f is nothing but partial derivative of f with respect to x1, first variable, comma partial derivative of f with respect to x2, okay, and so on, partial derivative of f with respect to xn. Just to clear the notation, this is just del of f divided by del of x1. This is del of f by del of x2, and so on. Okay. This is what is defined to be gradient. Okay, I think we will have some questions towards the end where we will solve these things, where will we actually calculate. One more thing. So we calculated this du hard way. Okay. So if you want to calculate du of f, that is directional derivative of u, right? In direction of u, you can simply do gradient of f multiplied by u. So this is dot product. This will give you this. So rather than doing explicitly for every direction, this is a common formula that you can use for anything. Okay. Now from this formula, you see one thing. Okay. So what is this dot product? This is norm of f, right, into norm of u into cos theta, right? Norm of u is 1 because we have taken unit vector. Okay. Now, let's say I want to maximize this thing. So I'm looking for a direction in which if I move, my function will increase the maximum. So directional derivative give you the change in function value if you moved in this particular direction, right? So I want to look for a direction in which I'll get maximum change. Okay. So how I can do that is that I can do only via this cos theta, right? Gradient is fixed. Norm of u is always 1. So I can only maximize cos theta. So what is the maximum value that cos theta can take? It can take value 1. Okay. So when does it take value 1? When the angle is 0 degree. So I want my angle between gradient of f and u to be 0 degree. What does that mean? I want gradient of f to be, sorry, I want my u to be gradient of f by, let's say, norm of gradient of f. Okay, I just want this direction only. Okay, so if you move in direction of gradient, your function increases by maximum. So if you move in direction of gradient, your function increases maximum. And if you are looking for a direction in which your function should decrease maximum, that is nothing but negative of your gradient. Okay. So you might have heard gradient descent, right? So gradient, descent is the because of this negative direction. So you move in negative direction of gradient in order to reach a minimum point of f. So if you move in the negative direction of gradient, you are moving fastest towards the lowest point possible. Okay. So this was about gradient. Okay. Now let's look at Jacobian. Okay. Now just a reminder, gradient was defined for a function from Rn to R. Jacobian is defined for a function from Rn to Rm. Okay. So your input is also, let's say, n dimensional, and you are getting m different outputs. Okay, you are getting something like f1, f2. These are different functions that you have stacked in an array, is a function of some strange kind of zeta function of, let's say, x1, x2, xn. Okay, this is what you will obtain. Okay, then in Jacobian, every row is a gradient. Let's say this first row f1 is gradient for f1, right? Second row is the gradient for f2. So this is del f1 by del x1. Second element would be del f1 by del x2, and so on till del f1 by del xn. Similarly, second row would be del f2 by del x1, and so on. So every row is a gradient. So this is what you define as Jacobian matrix. Okay. So before doing the question, let's look at what is Hessian matrix also. Okay. So just the intuition that if you look at gradient, we are calculating first order derivative, right? What I mean by first order derivative is, it is similar to calculating d by del f by del x, because we are calculating these only, but with respect to different variables, right? So Hessian is something similar to second order derivative. Okay, so this is like del square d square f by del x square. Okay, something like this. Okay, so what is the Hessian matrix? Again, Hessian matrix is defined for a function from R into R. Okay, R into R. So first row is okay. So first entry is del square f by del x1 square. Second entry is derivative with respect to x1, then with respect to x2. So these are all second derivatives. This would be x1, x3, right, and so on. This entry would be del square f by first with respect to x2, then with respect to x1, and so on. You complete this matrix of second derivatives. So this matrix is called Hessian matrix. Okay. So let's look at the examples that I have. Okay. So let J be the Jacobian of this particular function. Okay. So this is a function from R2 to R2. So you are getting two outputs, U and V, and you had two inputs, X and Y. Okay. Then at point 1, 1, what is the trace of the Jacobian? Okay. So let's calculate the Jacobian first. So Jacobian would look something like this is del U by del x1, right? Del U by del x2, great. Then you have del U by del x. Okay, sorry, this is del V now. Apologies. Del V by del x1 and del V by del x2, right? So what is this value? So this is x multiplied by y. Okay, so I can further change this notation because we have x and y. It's better to write it in terms of that. This is x, this is y, this is x, this is y. So if you take the partial derivative with respect to x, you will be left only with y. If you take partial derivative with respect to y, you will be only left with x. X square plus y square. You take the derivative with respect to x, you will have 2x. This is 2y. At point 1, 1, the value is 1, 1, 2, 2. What is the trace? Trace is equal to 1 plus 2, that is 3. Trace is, what is the trace of a matrix? Trace of a matrix is sum of its diagonal entries. Okay. Okay. So we have some more questions. So we have been asked to calculate the Hessian at this particular point. Okay. So how does my Hessian matrix looks like? So it would look like f of xx, right? Then f of xy, f of yx, and f of yy, right? I think I'm making sense. These two things are same. Okay. So first of all, let's calculate f of x. F of x is given by 3x squared minus 2y, right? F of y is given by minus 2x minus 6y to the power 5. Okay. Now we will calculate these values. What is f of xx? F of xx is 6x, right? The second term would go to 0. F of xy would be minus 2. F of yx again is minus 2. F of yy is this term goes to 0, so this is minus 30 y to the power 4, right? So what is the Hessian that I have? Hessian I have is, so at point 1 comma 2, so 1, this would be 6, this would be minus 2, minus 2. 2 to the power 4 is 16, 16 times 30. Okay. This is how you can calculate the Hessian. Okay. So this is what I had planned for today. If you have any doubt, you can ask now.